Hi everyone, my name is Iulia and I work at Google Research on natural language processing. In this presentation, we'll walk through the recent history of natural language processing, including the current state-of-the-art architecture, the transformers, and we'll also discuss how transformers became particularly successful when used in the context of transfer learning, which is a technique that leverages massive amounts of text. This tutorial is structured in 3 sections. First, we're going to talk about encoding text into a numerical representation that can be manipulated by machine learning models. Second, we'll discuss one of the most important tasks in natural language processing, namely language modeling. Among other architectures, we'll see how transformers solve this particular task. And third, we'll dive into transfer learning, which is the mechanism that enabled transformers to beat the state-of-the-art in natural language processing. And finally, we'll look at BERT, one of the most popular transformer models. So let's start by answering the following question. How do we encode text in a numerical format? Well, currently natural language processing is heavily machine learning driven. Most NLP systems follow this high-level contract where a piece of natural language text is input into a machine learning model, which produces a prediction that qualifies or describes the input in some way. This could be a discrete class, a real value, another piece of text, and so on. Let's look at sentiment classification, which is one of the most common NLP tasks. The input could be something like a TV show review from Rotten Tomatoes, like this positive review for BoJack Horseman. The expected output is a probability distribution over 2 classes, positive and negative, indicating how the author of the review perceived the TV show. In this section, we'll discuss the first part of this contract, namely how to encode a TV show review into a numerical representation that can be handled by the machine learning model. We can start with a naive view and just assume that words are discrete and independent tokens. One way forward would be to gather all of the unique tokens in a trading corpus and build a dictionary of tokens by sorting them alphabetically. Here, our first word is aardvark, and king and queen are somewhere in the dictionary. Remember, we want to convert text into numbers. So the first thing we could do is just to assign an index to each token, reflecting its order in alphabetical order. The problem is these very high numbers are not very amenable to machine learning and gradient descent in particular. So another thing we could do is use one-hot embeddings. These are vectors that have the same dimensionality as the dictionary. So if the dictionary has size 100,000, then a one-hot vector would have the same size 100,000, where only one of the entries would be 1 and all of the others will be 0. So for instance, aardvark has a 1 on the very first position and a 0 for all of the others. While one-hot embeddings do use values that are amenable to machine learning, they have 2 main disadvantages. First, when stored as dense vectors, have very high dimensionality, since they have 1 dimension for every entry in the vocabulary. And second, they fail to capture any world knowledge whatsoever about the tokens. In this particular case, king and queen have more in common with each other than they have with aardvark, yet all of these vectors have 90-degree angles between them. To see this more clearly, let's limit the vocabulary to only 3 tokens. In this case, the size of the vocabulary is 3, the dimensionality of the one-hot vectors is 3, so the words are vectors in a 3-dimensional space. With this one-hot embedding, words are unit vectors aligned against the axes. And there's an opportunity cost here. Why not allow the words to occupy the entire space as opposed to being perfectly aligned to the axes? A more practical view would be that words are continuous vectors in an n-dimensional space, so we'll allow queen, king, and aardvark to flow anywhere in this 3-dimensional space, So their representation contains real values like 0.3, 1.9, and minus 0.4. Before I move on, just a quick note on terminology. This way of embedding tokens comes under different names. It's known as continuous or distributed, embeddings, vectors, representations, and so on. So I will use these terms interchangeably throughout the presentation. Now, what sort of properties would we like these word tokens to reflect as we aim for them to encompass world knowledge? We can enumerate certain aspects that we'd like them to capture, such as gender or part of speech. Conceptually, various dimensions of the vector could be dedicated to each of these aspects. So, for instance, the first 3 dimensions could encode gender, and the next 3 could encode the part of speech. Of course, we will not enforce this particular attribution of meaning to the dimensions, but we can hope that the model discovers something of the sort. The mechanism that we use to express desired relationships is relative vector distance. For instance, on the gender dimension, king and queen should be as far apart as men and women. However, on the part of speech dimension, all of these words should be clustered together at a distance virtually 0, since they are all nouns. In contrast, play, which is a verb, and playful, which is an adjective, should be at the same distance as joy and joyful. So we've now enumerated the desirable properties of our embeddings and what sort of relationships we want to encode, but how exactly can we learn useful embeddings? Well, luckily the internet is free and contains a massive amount of information, and a good chunk of it is text. Even better, there's Wikipedia, which currently contains 28 billion words in 309 languages, which is a reasonably controlled and reliable source of information. Looking at the Wikipedia pages for king and queen, we can see a lot of commonality. They both reference each other, and they also include common words like monarch. Surely there's quite a bit of word knowledge that we can extract from here. Now, you might know that machine learning operates on pairs of inputs and outputs. A machine learning model is given some input X, and it has to produce a prediction that describes the input in one way or another. But Wikipedia comes in freeform text, so how can we gamify this text in order to have the model learn something from it? A common practice is to turn unsupervised text data into a supervised task. For instance, we could ask the model to fill in the gaps and predict the next word after a sentence like, "King is the title given to a male." The model could then produce a probability distribution over the words in the vocabulary, indicating which ones are more likely to follow the words so far. In this case, monarch would be a good candidate to fill in the gap. We'll now move on to discuss language modeling, or this gamification of unstructured text that allows us to learn from text even in the absence of explicit labels. Traditionally, language model is defined as the task of predicting the next word in a sentence. Given words 0 through n-1, the challenge is to predict the nth word. There are some variations on this traditional formulation. For instance, the context could be limited to the previous 3 words only, or instead of making a prediction based on the previous words, we could make a prediction based on all of the surrounding words, not just the ones to the left. So generally, language modeling refers to predicting a piece of text given some textual context. We'll discuss 3 main turning points in the history of language modeling: word-to-vec, introduced in 2013, recurrent neural networks, introduced in 2014, and transformers, published in 2017. Transformers are currently the state-of-the-art architecture for language modeling. Let's start with word-to-vec, the model that introduced distributed representations for language modeling. We'll now build a very simple language model that is inspired by word-to-vec. Let's start with a simple input like "on the river," hoping that the model will guess the missing word, which is bank. Just for simplicity, we'll limit our dictionary to only 5 tokens: bank, fish, on, river, and the. For now, we're going to start with randomly initialized embeddings. That's the best we can do. with no world knowledge at this point. The first step is to look up every word in the token embedding matrix. So now we've pulled out these two-dimensional vectors. The next step is to embed or aggregate all of these tokens into a wholesome view over the entire sentence. In order to predict what follows after 3 words, we sort of need to understand them together. The most simple thing that we can do is to average all of these embeddings together. Remember, this is a dummy model, so for now we're going to ignore the fact that it's not even capable of taking word order into account. Okay, so we've averaged these embeddings into a single sentence representation. Our end goal is to produce a score for every word in the vocabulary, indicating how likely it is for it to follow the sentence or the piece of sentence on the river.
How can we turn a 2-dimensional vector into a 5-dimensional vector? Well, the simplest option is a linear transformation using a 2x5 matrix. This is the role of the softmax parameters, which will be trained together with the rest of the model. Now, remember that the weights of the model are arbitrary at this point, and so are the scores it assigns to the 5 vocabulary tokens.
The next step would be to normalize them in such a way that all of them sum to 1, so they form a probability distribution. A common way to do that is to use logistic regression. In this expression, the red dots would correspond to the x in the formula. So now we have a probability distribution produced by the model, guessing what should come after on the river. It seems like the model is giving high probability to bank and for some reason also to on. How do we teach the model or tell it whether it made a good prediction? Well, we can peek at the word that should have been predicted, which is bank, and turn it into a probability distribution. So the true distribution, the one represented on the right, will assign probability 1 to bank and probability 0 to all of the other words. Having 2 distributions, we can now compute some sort of distance between these 2 distributions, and that can be done by cross-entropy. Once we have the distance between the 2 distributions, we can now backpropagate this error and tell the model how it can adjust the weights in a way that would have led to the correct prediction. This, in a nutshell, is how a language model is trained, and these principles will apply for all of the other language models that we're going to discuss. So while Word2Vec is an admirable effort and it really revolutionized the field when it came out, there are some disadvantages to this paradigm. One of them is that when associating a fixed embedding to a word, we cannot handle cases in which words have multiple meanings. So, for instance, the word bank in open a bank account and on the river bank would map to the same embedding. Ideally, we'd want these embeddings to be more contextualized to reflect the surrounding words around them. So open a bank account would have a different embedding from on the river bank. We'll now move on to recurrent neural networks, or RNNs, which provide a way of contextualizing embeddings so that words can be disambiguated based on their context. Let's trace the behavior of RNNs for an input sentence like, on the river bank they sat, where the task of the model is to predict the missing word sat. When building an RNN, we start off with non-contextual embeddings like Word2Vec that are looked up in a regular embedding table. In a sequential manner, we feed every non-contextual embedding into an RNN cell. The RNN cell has an internal state that it continuously updates as it progresses through the sentence, denoted by age on the slide. You can think of it as an encoding of the sentence so far. The cell produces a contextualized embedding Y based on its internal representation age, which captures the left-hand side context, and the non-contextual embedding of the current token X. For the word bank, this mechanism is particularly helpful. By the time the RNN reaches bank, it will have already seen the word river and encoded it in its internal state, so it's in a better position to disambiguate it from its other meaning of a financial institution. Once the final contextual embedding is computed, we can use the final internal state of the RNN to make a prediction for the next word. Just as before, we can add a linear classifier that maps the hidden state vector h5 into a vector with the same dimensionality as the vocabulary. After we get a score per vocabulary token, we can train the model using cross-entropy as before. While RNN encoders are great because they contextualize the word embeddings, there are certain disadvantages. The first one is that they are quite slow because of their sequential manner. If the embedding of word n depends on the embeddings of all of the previous words, it means it has to wait for them to be computed. So that's why the speed is O of n and the number of tokens. Another problem is the problem of vanishing gradient. This is another way of saying that by the time we arrived at the end of the sentence, we might have forgotten what the start of the sentence looked like. Because of this sequential processing, there's no way of revisiting very early tokens. And the effect of this structure might be that we learn very little from early tokens. A third disadvantage is that RNNs, most of them, are unidirectional, which means they process text from left to right, unlike humans. This is sometimes a problem when the relevant context is to the right. So we were lucky with a sentence like on the riverbank because river happened to occur before bank. But if we were to parse on the bank of the river, by the time we process bank, there's no information, there's no river, so we cannot disambiguate it from the financial institution. The third language modeling technique, which is currently the state of the art, are the transformers. And they address this problem of unidirectionality by teaching the model to take into account context both from the left-hand side and from the right-hand side of the sentence. Now, just for simplicity, in order to be consistent with the other models, I'm going to go through the transformer left to right. So let's see how the transformer works. As before, we're going to start with a sentence like, on the riverbank they, hoping that the model will fill in the blank. Note that this time, for the missing token, I'm passing a special token called the mask, and this is part of the vocabulary, so it's just like a regular token. The first step is to look up these words in an embedding table and get some non-contextual embeddings xi. These could be, for instance, word2vec. And then we're going to feed every token into a box that is called self-attention. Self-attention is one of the main building blocks for transformers. Self-attention works by taking into account or paying attention to all of the other tokens. So when embedding position 0, we do take into account all of the other positions 1 through 5. And the output, for now, we can see it as a weighted average of the tokens that we paid attention to. Self-attention comes with some terminology that will become easier to understand a bit later. The token that's currently being embedded is called the query token, and the tokens that we pay attention to are called the key tokens. The key tokens don't need to span the entire sentence. They could just span the next 3 words, for instance. But in general, most transformers do use the entire sentence for context. When we embed the word the becomes the query token, and all of the others are the key tokens. Same for river and bank. Let's take a step back and explain where the terminology comes from. To get some intuition about this naming convention, we can think of attention as a soft dictionary lookup. Say we have a dictionary dict mapping tokens to some value. When looking up the word bank in this dictionary, well, bank becomes a query. We'd like to retrieve not just the value of bank, that would be v3, but we'd like to get a weighing of all of the values, reflecting how similar their keys are to bank. Of course, the most similar word to bank is probably the word bank itself. That's why its weight will be 0.6. The next most relevant word is river because it disambiguates the meaning of bank, so it gets a pretty high score, which is 0.3. And all of the other words on the and they get some non-zero score, but pretty low. And finally, the mask itself has weight 0 because it carries no information. So this is just an aside to justify why the current token is called the query token and all of the others are called the key tokens. Now we're ready to open up the self-attention box and get some more clarity on what exactly happens inside. Self-attention has 3 model parameters. These are 2-dimensional matrices: the key parameters, the query parameters, and the value parameters. The terminology should already be familiar. Unsurprisingly, what the key parameters do is apply a transformation to the key tokens. So by multiplying a vector like x0 by a matrix K, we obtain another vector, key 0. Remember, these can be viewed as the keys into a dictionary. So we're going to put these aside for now. Let's move on to the query parameters. Let's see what they do. Well, also unsurprisingly, the query parameters transform the query token. So we multiply the non-contextual embedding of bank by this matrix in order to obtain some other embedding for the query. Let's put this one aside as well. I hinted a bit earlier at the fact that self-attention works as a weighted sum conceptually. Basically, we want to assign a weight to every single token in the sentence. And this weight should reflect the usefulness of a particular token in embedding the query token. We can do that by measuring the similarity between keys and queries. There are multiple similarity measures between 2 vectors, but most commonly, self-attention uses the dot product. So by applying the dot product between a key and the query, we get a scalar, which is the attention score and reflects how relevant a key is to the query. Let's put the attention scores to the side for now. The only remaining parameter that we haven't talked about is the values matrix. We're going to multiply the input tokens by this value matrix and obtain another set of vectors that's called the values. Referencing back to the previous slide with the analogy of a dictionary, you can think of these values as being the values stored in the dictionary. So each key has a value. Finally, what the self-attention box returns is a sum of these weighted values. Remember, the attention scores show the similarity between the key and the query, and they get multiplied by the values themselves. So the output is indeed a weighted sum of values. One implementation detail is that there might be multiple sets of keys, query, and value parameters. These are called attention heads. In this illustration, there are 3 attention heads. And having multiple attention heads is equivalent to having multiple kernels in computer vision. When processing an image, it's common to apply multiple effects like blurring, sharpening, or outlining in order to understand various aspects of the input. Language is a lot more abstract, so it's not trivial to describe what each transformation of each head is expected to do. But you could see how focusing on various linguistic aspects one at a time might be beneficial. For instance, one head might pay attention to parts of speech, while another head could focus on verb tenses. In other words, everything that we saw on the previous slide, we just perform 3 times. So we apply those transformations 3 times, we're going to end up with 3 outputs. What do we do with these 3 outputs? How exactly do we combine into just 1 output? Well, we can put a feed-forward network on top of the 3 inputs to just combine them back into one single output. And this is multi-headed self-attention. So let's zoom out of the box. I should have mentioned earlier that even though there's multiple self-attention boxes on the slide, all of them represent or are copies of the same box. So in this illustration, we would have only one set of parameters. You might have noticed already that self-attention is somewhat expensive. Since every token attends to every other token, that is O of n squared complexity. The good news, though, is that because this is not a recurrent neural network, processing input n does not need to wait on processing input n-1, n-2, and so on. All the dependencies refer to the previous layer. There's no arrows going in between the boxes, which means if we only depend on the previous layer, the only sequence that we need to respect is to compute things layer by layer. But within one layer, we can compute all of the token embeddings. So with the right hardware, even though we see O of n squared connections here, we could, in theory, compute all of them in parallel. So what's a transformer? We've only talked about self-attention so far. Well, self-attention is the main building block for a transformer, and a transformer is nothing more than a stack of self-attention layers. Each layer gets its own separate set of parameters. The transformer is also the first architecture to advocate for extremely deep networks. It's not uncommon for models to have 24 layers or more. So far, we've talked about how transformers turn non-contextual embeddings into contextual embeddings. The remaining question is, how exactly do we build a language model out of transformers? Well, one possibility is to pick one embedding output by the transformer, for instance, the first one. Remember that the transformer outputs one embedding, one contextual embedding for every single input in the sentence. But by the time we reach the top of the stack, all of these embeddings are so contextualized that they understand the entire sentence. So we can just arbitrarily pick the very first embedding and build on top of it. Previously, for word2vec and for RNN, we just used a linear transformation to map an embedding into scores for every word in the dictionary. That's exactly what we're going to do here and produce one score for every word. Now, the transformer encoder is a complicated piece of machinery, and we've talked about it from a very high level perspective. There are some implementation details that are crucial to making it work, but they were not included in the slides. These include residual and skip connections, layer normalization and dropout, and so on. I invite you to read the original papers if you're interested in that much detail. While transformers are the state of the art for language modeling, they come with their disadvantages. Of course, there's this computationally intensive work, number of layers multiplied by n squared, where n is the number of input tokens. This could be alleviated by hardware that can perform certain operations in parallel, like TPUs, but on normal hardware, this is very expensive. Another downside is that transformers require a fixed number of tokens. In other words, the length of the sentence needs to be set when designing the model. It's very common for all of the inputs to be set to 512 tokens. So if the input sentence is longer than that, it has to be truncated, and if it's shorter than that, it has to be padded. This concludes our discussion about language models. We visited 3 different approaches to language modeling. Word2vec brings the innovation of continuous word representations, which are superior to one-hot encodings because they can encode world knowledge and also have lower dimensionality. RNNs made these embeddings contextual, that is, aware of their left-hand side context, so that a brick-and-mortar bank is assigned a different embedding from a river bank. And finally, transformers ensure that embeddings are bidirectional, and they're aware of both the left-hand side and right-hand side of the context. So for instance, in the phrase, the bank of the river, the meaning of bank is determined by river, even though river is to its right-hand side. In the final section, we'll discuss the concept of transfer learning and one of its most successful applications, the BERT model. There's a wide range of NLP tasks, from sentiment classification, named entity recognition, question answering, machine translation, and so on. The common thread across all tasks is that they require some general knowledge about language. For instance, knowing when something is a verb or a proper name is useful regardless of the exact application. Transfer learning was born based on the observation that it's a lot more effective to acquire this knowledge once and reuse it in all of these applications. This is similar to how humans behave. We learn to speak in childhood, and then we carry this knowledge throughout our lives, adapting how we speak to various situations. In machine learning in particular, we also face the challenge of limited label data. Labels are most of the time produced by humans, and human labor is time-consuming and expensive. If your goal is to build a sentiment classification system for movie reviews, having someone sift through every review and decide whether it's positive or negative is very laborious. Not to mention that in certain cases, a lot of expertise is required. For instance, if you want to build a system that translates natural language into executable code, you need a programmer to produce training examples. The philosophy of transfer learning is to leverage very cheap, unstructured data that is readily available online to pre-train a model so that when it's presented with the scarce labeled data, it hits the ground running. The most popular paradigm for transfer learning is pre-training and followed by fine-tuning. It consists of two training stages applied sequentially. First, we train a general-purpose model using unstructured data from the internet, usually with a language model objective. And then we continue training it on the label data and specialize it for a particular target task. This technique is currently the state of the art across the majority of natural language applications. Let's revisit our initial task of automatically detecting whether this TV show review from Rotten Tomatoes is positive or negative. When we initially asked the question of how to encode the text in a way that a machine learning model can process it, we agreed that using continuous vector representations for each token was the way forward. The next challenge was to learn these embeddings in a way that captures meaningful semantic relationships between words, and we agreed that Wikipedia was a good source of linguistic and world knowledge. We then discussed three language models that gamify unstructured text by predicting the next word in a sentence. So the remaining piece of mystery is, once we've trained a language model, how exactly do we leverage it in order to solve our original task? How do we do this transfer of knowledge? A potential answer is the sequential paradigm of pre-training followed by fine-tuning. Next, we're going to talk about how exactly this arrow is implemented. We're going to start off with a transformer stack. This transformer learns a language model when inputted inputs like the king is the title given to a male blank. So its goal is to figure out what exactly is hiding behind the mask. This stack contains an embedding table with non-contextual continuous representations, followed by a transformer encoder that contextualizes these embeddings. And at the end, the model will predict a token, hopefully monarch. What we do in the pre-training and fine-tuning paradigm is take a copy of the model that we just learned using a language model objective. So we've just copied over the embedding table and the transformer encoder. How exactly do we use this model, which only knows how to do language modeling, to do sentiment classification? Well, we add a classifier on top, which could just be a linear transformation, and these are newly added parameters. This classifier is able to ingest some contextual embeddings produced by the transformer encoder and output the desired label. When training on the label data, now we fine-tune the entire stack. So remember that the embedding table and the transformer encoder were already in pretty good positions. We just copied them from a model that can do language modeling. The only randomly initialized bit of the model is the classifier. When we do training on the sentiment classification task, we update all three components of the model: the classifier, the transformer encoder, and the embedding table. The hope is that because the embedding table and the transformer encoder, which contain most of the parameters, are already in a pretty good state, this fine-tuning process is relatively lightweight compared to full pre-training. Finally, we'll talk about BERT, which stands for Bidirectional Encoder Representations for Transformers, which is just one instantiation of the transformer architecture. BERT was trained at Google on Wikipedia data with a language modeling objective. BERT is readily available for download on multiple platforms, including GitHub, TF-Hub, and Hugging Face. There's multiple models. The ones in English come in different sizes. The smallest model has only 2 layers and embedding size 128, and the biggest one has 24 layers and embedding size 1024. So there's quite a huge range of models. There's also a model in Chinese and a model that is multilingual and supports 104 languages. The multilingual model is pretty impressive because you can feed in input in any of the 104 languages, not even specify what language you are inputting or what language the input has, and it will probably do the right thing. How do we use BERT in a downstream task? Well, there's multiple classes of tasks, and each of them comes with its own special use case. The simplest class of tasks is single sentence classification. For instance, sentiment classification. Given a movie review, we have to output a label, either positive or negative. Here's how we can use the BERT stack. So remember, the first step was just to copy BERT, download it as it was made readily available by Google, and then add a classifier on top. There are some implementation details that come with BERT that I want to dive into. If we look at the bottom of the diagram, you'll see that in addition to the input tokens, the single sentence that we're inputting to the model, there's a special token called CLS. It stands for classification. This is a special artificial token that we add to our vocabulary to mark the beginning of a sentence. The rest of the stack works just as a normal transformer encoder would do. At the bottom, we have the non-contextual embeddings, and at the top, we have the contextualized embeddings. What exactly do we feed into the classifier? Well, in all honesty, we could feed any of the top embeddings because all of them are fully contextualized and they're aware of the entire sentence. But there might be localized to the meaning of a particular token. So to get around that artifact, we can simply take the embedding of the CLS token, which, remember, it does know about the meaning of the entire sentence because at the top of the network, everything is fully contextualized, but it doesn't particularly focus on one word of the sentence. So if we feed the embedding of the CLS token into a classifier, we can then get a prediction for our end sentiment classification task. Another class of natural language processing tasks is classification, where the inputs are a pair of sentences as opposed to a single sentence. Paraphrase classification is one example. You're given 2 sentences like, "She accepted immediately," and "The woman did not hesitate to accept." And the task is to decide whether these 2 sentences are paraphrases of each other. As before, we just make a copy of the BERT model that's readily available online, and we add a classifier on top. The detail that I want to emphasize is the fact that there's a special separator token that is added in between the 2 input sentences. Just like CLS, this is a special token that's added to the dictionary with the purpose of marking the end of one sentence and the beginning of the other sentence, so that the models knows what tokens fall into the first sentence and what tokens fall into the other sentence. And finally, another class of natural language processing tasks is span annotation. This refers to the fact that we need to make a classification or a decision at every point in the sentence. Part of speech tagging is one example. For a sentence like "she accepted immediately," we want to tag every single word with its part of speech. So she is a pronoun, accepted is a verb, immediately is an adverb. Same story, we copy the model as it's readily available to download. And of course, we're going to need a classifier, but how do we use this classifier in a way that it makes multiple predictions? Well, we're just going to pass every embedding in the sentence one by one through the classifier. Let's say that T1 corresponds to she. We pass the contextualized embedding of she through the classifier and produce a label. Similarly, let's say T2 corresponds to accepted. We pass the contextual embedding of accepted through the classifier and hopefully get a verb label. And so on for the entire sentence. So now we've visited three main categories of downstream tasks that can be solved by simply fine-tuning BERT. Here's a piece of code that shows you how to do that in practice. BERT is available on multiple platforms, TF Hub being one of them. TF Hub is particularly easy to use because everything you have to do is provide a URL with the model that you want to download. So we're going to use the Hub library, and we're going to ask TF Hub to download the model from this specific location. In my case, I'm choosing a very small model because I don't want to wait a long time for it to get downloaded, and it has sequence length 128. The API of this library requires me to define what the inputs to the model look like, or what are the placeholders where I'm going to feed in the input text. And these can be defined as Keras inputs. The next step is to extract the CLS embedding from the BERT outputs. Remember that if I want to do sentiment classification, I need to take the contextual embedding of the CLS token and pass it through a classifier. Once I take the CLS embedding, I can define my own classifier. In this case, the classifier is a dense Keras layer with 2 units because the sentiment classification task has 2 possible classes. And finally, I pass the CLS embedding, the contextual CLS embedding, through the classifier, and I define a model that takes as inputs whatever I feed into BERT, and it takes as outputs whatever the classifier outputs. At this point, I'm ready to just call model.fit and train my model. Because BERT was quite a success story, it inspired quite a bit of follow-up work. There are models that revisit the training process and make it more robust, like Roberta. There's a lot of research that has gone into preserving the accuracy of BERT, but shrinking it or making it faster for inference. And this is the case for Albert, MobileBERT, TinyBERT, and a lot of other models. There's also language-specific models trained specifically for French, Chinese, and so on. Most of these are, again, readily available to be downloaded, and you can build your own model by simply fine-tuning them. This concludes our journey through the recent history of natural language processing. As of today, transformers remain the preferred architecture for most NLP tasks, and pre-training and fine-tuning, the paradigm itself is ubiquitous. The biggest roadblock that we're facing today is that transformers require a fixed input length. And because of their computational complexity, they cannot be effectively scaled beyond a few hundreds of tokens. The solution might come either from specialized hardware or from innovations on the modeling side. Either way, natural language processing remains a very interesting field for research and for industry applications. Thanks for your attention, and make sure to check out the other videos in the series.